Hello everyone, I'm Professor Ricardo, and in this video we are going to solve a quantum mechanics problem. This one is a problem of the book Modern Quantum Mechanics by Sakurai. We need to show that the determinant of a 2x2 matrix, sigma A, is invariant under this transformation. You have sigma A here and then sigma A prime, which is a product of all these matrices, sigma A and then this exponential with a positive sign and this one with a negative sign. And then we need to find AK prime in terms of AK, where AK and AK prime are the components of the vectors A and A prime. When in a particular scenario where this unitary vector n is in the positive z direction, and then we are going to interpret our results. So what is the scalar product of sigma and A? It is the product between A and the Pauli matrices, sigma 1, sigma 2, and sigma 3. You may call them sigma x, sigma y, and sigma z as well. So you have here that sigma A is equal to A1 sigma 1 plus A2 sigma 2, and so on. And explicitly in a matrix representation, in the diagonal elements you will have A3 multiplying 1 and minus 1, so you will have here A3 and minus A3. The off-diagonal elements are coming from these two terms, A1 multiplying sigma 1 and A2 multiplying sigma 2, so you get A1 minus I, A2, and here A1 plus I, A2. And then it's easy to calculate its determinant. The determinant of sigma A is going to be minus A3 squared minus the product between these two elements here. A1 squared, the cross terms will cancel out, and then you have minus I multiplied by I, which is plus A2 squared. And then you get this result where the determinant is minus A squared. What about the determinant of sigma A prime? If they are equal, then we know that the determinant is invariant under this transformation. Okay, then we need to calculate the determinant of this term, which is a product of these terms. And let's remind ourselves that the determinant of a product of operators is the product of the determinants of each operator. Then the determinant of this sigma A prime will be the determinant of this term, the determinant of sigma A, and the determinant of this exponential here. At the end, we need to find what is the determinant of this exponential with positive and negative of this argument. And if we need to calculate the determinant of this matrix, let's find what is this matrix. We know that the exponential of an operator, for instance x, is defined as 1 plus x squared over 2 factorial, and so on. And using index notation, we can write this as the summation from 0 to infinity of x to the power of n, capital N, over n factorial. So instead of x, we have this argument. And then we're going to write it as the summation from 0 to infinity of plus minus I, phi over 2 to the power of n, this matrix sigma n to the power of n over n factorial. Okay, now, what is sigma n, where n is a unitary vector? In index notation, we can write it as the summation of ni sigma I. In other words, will be n1 sigma 1 plus n2 sigma 2 and plus n3 sigma 3. Let's keep this result here. And then, what is sigma n to the power of 0? And what is sigma n to the power of 1? They are obviously the identity, and here will be the sigma n itself. Okay, so I guess you've got the idea here. We are going to find some of these terms. Maybe we can find a pattern. So sigma n squared. We need to calculate that, and since sigma n is this summation, we have here a product of these two summations. Obviously, we need to change the index of the summations, as one can see in this video here, where we discuss index notation and Levi-Civita tensor, Kronecker delta, and many other aspects of tensor notation. And then we can write this as a double summation over I and j of ni and j sigma I sigma j. So we have here a product of two Pauli matrices. And in this video, we investigate some properties of the Pauli matrices. One of them is related to the product of two sigmas. Sigma I sigma j is the delta, the Kronecker delta ij multiplied by the identity plus I, the epsilon, the Levi-Civita tensor multiplied by sigma k. So this result is very straightforward. When I and j are the same, then the Levi-Civita symbol is 0, and this delta is 1, resulting in the identity, which is what we expect. Sigma I squared is equal to the identity. For instance, sigma 1 squared is the identity. And when they are different, then the delta is going to be 0, and the epsilon, the Levi-Civita tensor, is going to be +1 or -1, depending on if it's a cyclic or anticyclic sequence of I, j, and k. So, for instance, sigma 1 and sigma 2 multiplied, this is equal to I sigma 3, which is exactly what we expect. Okay, so since sigma I sigma j is equal to these two terms, so we are going to write this summation into two summations. The first one will be ni and j times the delta ij and the identity plus ni and j I, the epsilon, sigma k. Okay, so when we use the summation over j, for instance, when j is equal to I, then this delta is going to be different to 0, is going to be 1 when j is equal to I, and we will get the summation on I only of ni squared times the identity. And then we will have this other term. But before doing that, we already can note that this term is equal to 0, is equal to 1 actually, because this is a unitary vector. Okay, and this is exactly what we expect. We can recognize that it is I times the outer product of n and n in a scalar product with sigma. So this is obviously 0, because you have this outer product between n, and then sigma n squared is equal to the identity. Okay, now let's try to find a pattern among even and odd values of n. If you calculate sigma n to the power of 3, then we can easily calculate that multiplying this equation by sigma n. If you do that, you will get on the left-hand side of the equation sigma n to the power of 3, and it will be equal to sigma n. Okay? And if you repeat multiplying this equation by sigma n, you will have sigma n to the power of 4, and it will be equal to sigma n squared, but sigma n squared is equal to the identity, and so on. So for every even value of n, you will get the identity, and for every odd value of n, you will get sigma n. Let's keep this result here, and then we can write this as two summations. I'm going to repeat this argument, but now I'm going to distinguish between two summations. The first one is a summation over even values of n, and the other one is over odd values of n. Okay, so the idea here is, since we know that sigma n to the power of even values, all of them are equal to the identity, so we can write the identity as a factor, and then we are going to calculate plus minus I over, to the power of 0, when n, capital N, is 0, this is going to be 1. Phi over 2 to the power of 0 is 1, and then over 0 factorial, which is 1 as well. Okay, when n is equal to 2, so we will get I squared, which is negative sign here, minus I squared is the negative sign as well. So you'll have 1 over 2 factorial, phi over 2 to the power of 2, and when n is equal to 4, you will get, since I squared is minus 1, then I to the power of 4 is going to be plus 1. So you get this positive sign, the same considering the negative 1 here. 1 over 4 factorial, phi over 2 to the power of 4, and so on. Every factor will have this identity. Every term will have this identity as a factor. And before calculating this, we already can recognize this sequence as the cosine of phi over 2 multiplied by the identity. So the other term, all terms will have sigma n as a factor. So when capital N is equal to 1, we will get plus minus I, 1 over 1 factorial, phi over 2. And then the next one will be plus minus I to the power of 3, which is going to be I squared multiplied by I, which is minus I. And for the other sign, will be I squared multiplied by minus I, which is plus I. 1 over 3 factorial, phi over 2 to the power of 3, and so on. Every term multiplied by this matrix. And then we can recognize these terms in green as plus minus I sine of phi over 2. And this term is multiplied by sigma n. Great, so now we know what is this exponential. It is equal to this. And how can we calculate the determinant of sigma a prime? It will be since sigma a prime is a product of matrices, the determinant of it is going to be the product of the determinant of each term, of each matrix. So the determinant of this exponential with positive sign, the determinant of sigma a, and the determinant of this exponential with a negative sign. Okay, so we need to find these determinants. And then let's write this matrix in a matrix representation. So the first term here is cosine of phi over 2 multiplied by the identity, so you get the diagonal elements here. And before writing this term, let's observe that sigma n is equal to n3 minus n3, diagonal elements, n3 multiplied by sigma 3. And then n1 multiplied by sigma 1 will give us this n1 and n1 here, the off-diagonal elements. And n2 multiplied by sigma 2 will give us minus I n2 and plus I n2. Okay, so now, since we have this factor multiplying sigma n, we will get plus minus I sine of phi over 2 multiplied by n3, the same multiplying minus n3, that's why we get here minus plus, and then the same term multiplying n1 minus n2 and n1 plus I n2. Okay, let's sum these two matrices, and then we get this, the diagonal elements are going to be the cosine plus minus this term and the cosine minus plus this term. Okay, now it's easy to calculate the determinant. The determinant is going to be the product of these two terms minus the product between these two terms. So we will get the cosine squared of phi over 2. Then, multiplying cosine by this term, we will have minus plus I cosine of phi over 2 multiplying sine of phi over 2 and 3. And this term multiplying this term will give us a similar term, but with opposite sign. Then they will cancel out, even when we are considering the positive exponential or the negative on this exponential. The next term is going to be plus, with this minus, you have a minus sign, but then you have I squared, which will give us another minus sign, negative sign. So then you will get positive, and the same for the other term. Sine squared of phi over 2 and 3 squared. And then minus the product of these two terms, which will be negative of sine squared of phi over 2, and then this term multiplying this term, which will be n1 squared. The cross terms will cancel out, and then minus I times I will be positive n2 squared. Great, so sine squared of phi over 2 multiplying n1 squared, positive sign, plus n2 squared plus n3 squared. And this is equal to 1 since n is a unitary vector. Then we will get cosine squared plus sine squared, which is equal to 1. So the determinant that we are looking for, even for the exponential with a positive or negative signs, this determinant is equal to 1. So here, this is equal to 1 and this is equal to 1. And then the determinant of sigma A prime is equal to the determinant of sigma A. We conclude that this transformation makes the determinant of this matrix invariant. Now, let's find AK prime in terms of AK in this scenario. And what is this scenario? It is when n is in the positive z direction. In other words, instead of considering a vector with components n1, n2, and n3, you have only n3. And since it is a unitary vector, n3 is equal to 1. So, in other words, what we are going to do here is we are going to write again the exponential term that we got in a previous slide, and we are going to write n1 and n2 equal to 0 and n3 equal to 1. The first term, we will get cosine of phi over 2 plus minus I sine of phi over 2, and we can recognize this as an exponential, as we are going to do soon. This term will be the same idea, and these, the off-diagonal elements, are going to be 0. So, cosine of phi over 2 plus I sine of phi over 2 is the exponential of plus I phi over 2. We can write these terms as an exponential. And when it is the negative sign here, the exponential will be of minus I phi over 2. So much easy. Sigma A prime will be this matrix with a positive sign, so the exponential of positive I phi over 2 and negative I phi over 2 multiplied by sigma A, which is A3 minus A3, as we already did in a previous slide, and multiplied by the exponential of negative sign of this argument, which is going to be the exponential of minus I phi over 2, and here the exponential of plus I phi over 2. So we need to do the product of these three matrices. Calculating the product of these two matrices, we will get A3 multiplied by this exponential, then this term multiplied by the exponential, this exponential, then the second line by the first column, we will get this term multiplied by the exponential with negative sign, and then the second line by the second column will result in minus A3 multiplied by this exponential. And then we need to multiply by this. And when we do that, we will have A3, the exponential with a positive and here a negative sign will be 1, and then A3. And then the first line by the second column, we will get A1 minus A2 multiplied by the exponential with a positive sign and the same, then it will result in the exponential of plus I phi, not phi over 2 anymore, but phi. The second line by the first column will result in this term, and then the negative, the exponential of this times the exponential of this argument will result in the exponential of minus I phi. And then the second line by the second column will result in minus A3. Okay, but sigma A prime is A3 prime minus A3 prime on the diagonal elements. And the off-diagonal elements, they are A1 prime minus I plus I times A2 prime. Okay, and this is equal to the matrix that we already just found. Then we are going to compare the elements and try to obtain information about the AK prime in terms of AK. The first one is very straightforward. A3 prime is equal to A3. This is our first result. The other ones, A1 prime minus I A2 prime is equal to this term. And then A1 prime plus I A2 prime is equal to this term here. If we sum these two equations, we will get 2A1 prime being equal to A1 as a factor multiplying the exponential with positive sign plus the exponential with negative sign minus I A2, this is the factor we are going to use, and then we are summing these two equations. So we will have the exponential with positive sign, but since we included minus as a factor, then we will get this minus here, the exponential with negative sign. And when we subtract them, these two equations, we will eliminate A1 prime, and then the result is going to be 2 times minus I A2 prime being equal to A1. And then we will get the difference between these two, minus I A2, and here we will get the sum of these two exponentials. So now, what is the sum of these two exponentials? So these, the sum of them will eliminate the term, the imaginary term containing the sine of phi, and we will get 2 times the cosine of phi. And when we subtract them, we will eliminate the real part of these exponentials containing the cosine of phi, and we will get only the imaginary part. So it will be 2 times I sine of phi. We will use these two equations in this result, and the first one, dividing all of them, every term by 2, we will get a1 prime being equal to a1. Then, since this is 2 times cosine of phi, we already divided every term by 2. This results in a1 cosine of phi. The other term, we will get a2. This will result in 2i sine of phi. And the product between minus I and I will result in plus a2 sine of phi. The second equation, we will eliminate this term minus 2i on every term, and then the result is going to be a2 prime being equal. First, let's do this. Will be a2, and this will result in a cosine of phi. And this one we will get a1 minus the sine of phi, because we eliminate minus 2, and here we will have 2i a1. Okay, so we get these two equations here, and this is the answer. This is what we were looking for. We just found ak prime in terms of ak. And what is this? What is the interpretation of this result? This is obviously a rotation about the z-axis, because there is no change on the a3 term, which is the az prime being equal to az. So this is a rotation about the z-axis, and it is a counterclockwise rotation of an angle phi. So if you do a rotation about the z-axis of an angle phi, you will get this result here.